Okay, good morning. I'm going to try recording a quick little video here to talk about what we were going to talk about in today's class. Sorry for the issues with virtual classroom, not sure what was going on with that. So like I said, we're talking about oscillatory motion in this topic. So oscillatory motion is defined as some sort of a repetitive motion that is going back and forth across an equilibrium point. And there's several different examples of what sort of oscillatory motion we see. So for example, any sort of vibrations, we'll call this example. Some examples of this are vibrations. Such as, for example, guitar strings or something that are vibrating, bells or something that vibrate when you ring a bell, and like I had mentioned before, lots of machinery is something where you have to consider how it is vibrating. Other topics that we look at, especially here in Physics 20, are pendulums and masses on springs. And so in both of these cases, we've got some sort of a repetitive motion that is moving back and forth across an equilibrium point. If we're talking about pendulums here, for example, say we have a pendulum that is attached to the surface, and this pendulum can swing back and forth. Well, of course, our equilibrium point is going to be right down the middle here. That's where the pendulum will naturally come to rest. Equilibrium. And so if I pulled this pendulum to the side here, well, it would swing back towards the middle, and it would swing back to over here. And it would keep on repeating this over and over and over. If we're talking about masses on springs, well, then we've got kind of the typical situation is we have a spring with a mass attached to it. And this, again, if you let this spring just go naturally, well, it's going to sort of settle at an equilibrium point. If you were to pull on the spring, well, the mass would get stretched out to over here somewhere, and it would go back and forth between that point and a point over on this side of the equilibrium. And it's going to go back and forth and back and forth. And we're going to talk about this in a whole lot more detail, so I'm not going to go over it too quickly here. In too much depth here. One specific kind of oscillatory motion that we are going to talk about here today is what we call simple harmonic motion. And so when we're talking about simple harmonic motion, and in fact, really this is all we're going to talk about in this unit. The important sort of specification about simple harmonic motion that makes it different than oscillatory motion is that the force causing it to return to equilibrium is proportional to the displacement. And we're going to talk about what this means here in a minute. Displacement from equilibrium. So basically, the further you are from equilibrium, the more force there is trying to get the object back to equilibrium. And so we're going to talk about what this means for both a spring as well as for a pendulum. Sorry, one other thing I wanted to mention just before we get into this, just a reminder, so we said that oscillatory motion is something that is repetitive. So really that means that it has a period. So a period is the length of time for one cycle. So of course, period, remember, was capital T, and we measured that in seconds. And that's also very closely related to frequency. Instead of length of time, I'll say amount of time. Frequency, which was the number of cycles per second. And we said that was F, and we measured that in hertz. We're going to be looking at period and frequency pretty much all the time in this unit. So we're going to have to get comfortable using these, and again, we're going to have to get comfortable moving back and forth between frequency and period. And remember, they are just inverses of each other. Okay, so let's talk about springs first here. So we'll talk about spring mass systems. And first of all, so we'll call this case A. We'll talk about what happens if they are horizontal. Horizontal ones are typically a little bit easier to think about, because once we're looking at vertical ones, then we start to have to worry about gravity. All right, so like I drew above, we'll draw another little picture here. We've got a spring with a spring constant. Remember, this is the spring constant. And the spring constant is something that we measured in newtons per meter. It's basically a measure of how stiff the spring is. Does it take a lot of force to stretch the spring, or is it easy to stretch? That's what the spring constant measures. And then we've got an object with some sort of mass, and it is sitting at our equilibrium point here. So, like we said, once we let go of this system, it's just going to stay at its equilibrium point. So this is the position that it naturally comes to rest at. Well, what happens if we stretch the spring out? So let's say we've stretched the spring out here, and our mass is over here now instead. We still got the same spring constant, same mass. Our equilibrium point is still the same. Well, what's going to happen to this mass? Well, we can think about this. Naturally, what happens here is that the object is going to want to return to its equilibrium point. And what's going to cause it to return is a force. So there's going to be a force here causing this spring to return. And the more you stretch the spring out, the greater that this force is. We call this a restoring force because we're trying to return it to equilibrium. We're trying to restore the equilibrium, but really it's a net force. What is the net force that is causing this to return back? And you know what? I should fix my drawing here because really this spring, this mass is sitting on a flat surface. And we're assuming it's a frictionless surface. We aren't going to talk about friction at all in this whole unit. We're assuming everything is frictionless because things get quite a bit more complicated once you include friction and you need to get into calculus and things like that. And we aren't going to do that here in Physics 20. So like I said, there's this restoring force that is pulling it back. And the biggest question that we have to ask about a restoring force like this is, what is the magnitude of the force? How big is the force that is pulling it back? And that's where something called Hooke's law comes into play. So Hooke's law is basically saying how big is the force that's caused by a spring. And it basically says that the force of a spring is a very simple formula. It's equal to the constant for the spring multiplied by the distance that the spring has been stretched. So I'll add x onto my diagram here. So x is the distance that the spring has been stretched. So when we're talking about spring mass systems, we're going to get into cases like once we pull it to the side and then let go, it's going to sort of bounce back and forth. For now, we're just talking about, okay, when I just pull it to the side, how much force did it take to get to that point? And how much force is going to try to pull it back to the middle. The negative sign here, it really just indicates that we're trying to get back to equilibrium. Most of the time, you're just going to naturally account for this negative sign, and you aren't going to have to worry about the direction too much in this topic, but it's always going to be there. So this is Hooke's law, showing how the force of a spring and the distance that it is stretched are related. And remember, up here we said that simple harmonic motion, which is the type of motion that we're talking about here, is when the force is proportional to displacement. So we can see in this equation here, our force is directly proportional to the displacement. So, for example, how do we use this equation? Let's look at a quick example here. Let's say how far from equilibrium would a spring get stretched if a 12 Newton force is applied? And we know the spring constant is 25 newtons per meter. Well, this question is not too difficult. We know our force is 12 newtons. This is obviously going to be the spring force. In this case, it's going to be the restoring force as well. Well, we know our constant is 25 newtons per meter. And we're looking for the distance that it's been stretched from equilibrium, which is just x. So of course, force of the spring is just equal to negative kx. Our force here is 12 newtons. 12 newtons, sorry, I'll write out my formula here. Is going to be equal to force divided by k. Like I said, we aren't going to worry about the minus sign too much here because obviously the force is pulling it back towards equilibrium. So this is 12 newtons divided by 25 newtons per meter. And when we calculate this, we get 0.48 meters is all it's stretched from equilibrium.